Hello, everybody. Thank you for being here. I hope that the pizza was good. So I'll present myself. My name is Olivier. I'm a co-founder of Moov AI. Moov AI is a consulting company in data science. We are about a year old, so this is why you might not have heard of us, but we're working on making sure that this good technology, machine learning, data science, all those tools that really help to automate decisions are being used by companies. So this is what we're doing. And before I start my presentation, just want to know who here is a junior data scientist or someone like someone who is acquiring new knowledge. Okay. And who's intermediate or advanced in data science? Okay, great. Perfect. So I'll cover, don't worry, there will be a lot of stuff for people who just started. And also I'm covering some content that is more advanced. I'll try to keep it as simple as possible, but sometimes the concepts might be a little bit more complex. Well, okay, so the objective of today is to first discuss about the importance to validate. So this is pretty basic, but we'll cover also some techniques. So what do we need to do to validate that things work? It's easy to say, you know what, I did some Kaggle, it worked. So if I want to deploy a similar project in real life, it will work. This is not true, rarely true. And this is what we're going to tackle today. So first, this one, when we started Moov AI, I knew from experience that projects rarely go forward, rarely bring benefit, but I didn't know to that extent. So this comes from, it says basically that most projects that we build, most proof of concepts are never deployed, or when they're deployed, they don't bring any value. So this is pretty bad. So 9 out of 10 projects never bring any value. If we're thinking about our industry, what it might mean is if we're not doing anything, we might be shut down, because it's a lot of money that people spend every year to get teams and data scientists pay the big price to try to deploy something, and most projects will never bring value. So here, this is why when I thought about it, I said, there's something that might help. It's not the key, it's not the answer. There are a lot of different answers on how to prevent that, but one way is to make sure that we have the right validation in place. So at least the proof of concept that we build have a fighting chance to be deployed and to bring value. And so concretely, what it does first, it assess the project. Is it crappy? Is it the crappy project? It doesn't work. It's super bad and it doesn't bring any value. So at least when you test it right, you know that. Okay, it's not always like a sunny day scenario where something and it's game changer. Sometimes it's not the case. Also, it makes people more confident about your project. Maybe you have a super good project, but before the previous presentation, the presenter talked about all the different teams the data science has to convince. And it's hard to convince by showing, rock curves and, oh, it's 92% confidence, like my accuracy, my AUC is such and such. It just doesn't work. You need to be able to demonstrate something. You need to be able to give confidence. And also the last point I want to cover is sometimes it's also just required. In the banks, there are some regulation bodies. And even when it's not required, it should be. So I'm expecting in the next couple of years that we're going to have like a regulation body that will, or at least should, validate a lot of the most important models that are being deployed. Okay, cool. So here I really wanted to use this corporate thing, so I decided to use an iceberg, and you'll see quickly that it's not just an iceberg, but it's also a funnel. So it's like double corporate. And no, I'm just kidding. But this is I call it the iceberg of fails. So when we talk about the 87%, this is the like no results. Doesn't work. The data science team is not working properly. We should fire everybody. We should close that, that kind of stuff. But underneath, so we'll see 3 different types of errors that we always do. So the first one is adoption fails. We work on a proof of concept, but we never inform the team. When the team is testing, so the end users, people in businesses, and like a beta testing with real users, they find the results weird. Even if it's maybe not weird, but just the fact that it feels wrong sometimes might break, the confidence of the full team who should approve what you're building. For instance, for Uber, or not necessarily Uber, like if you're looking at Tesla and the autonomous vehicle, every crashes are getting communicated, and people are bashing on the autonomous vehicle. But in the aggregate, it's pretty good to only have those amount of crashes. But we need to gain the confidence. We're not starting equal to the old ways of doing things. Then we have the technical fails. This one, we know it, we learn from it, but I'll go even deeper in this one because we're often just superficial in the way we're looking at it. We should not just look at accuracy, for instance. And so I'll cover that. And finally, one of the most hidden risk, but one of the worst risks is the project fails. So you try to work on the wrong projects. So here, when we're looking at the project development, this is what we're using at Moov AI. The only difference is we decided to stop working on proof of concepts. We're only working on, so here we should say, MVP, but anyway, it communicates the right thing. So first we start with ideation, and then we do a kickoff. So making sure that we work the proper way on the project. We create, the project management documentation. And then we start working on the project. And when we're confident about it, so we demonstrate something, we do sprints, and at some point we say, okay, you know what, we have it, but we need to deploy it in real time on the regular systems. So we build the API, the integration, the dashboards, or the integrations. And then when it's fully deployed, we're super happy. But then comes the time to monitor what we do, making sure that whatever is being deployed gets validated in time, because it's not just sit and forget it. So when we're looking at project validation and when it should happen, so at the beginning, it's not just brainstorming about ideas and then starting thinking about like the PO, who's the PO, what's the budget, okay, let's go forward. So we need to think about the risks. I'll show you a couple of questions that we ask, but essentially it's just about understanding really well the problem from the user's perspective. Then after that, when we continue the work, the process, we start defining and preventing some technical risk along the way. But we have to validate the deployment prior to deployment. So this is where it happens. So we do 2 validations. One, when we essentially build a script, so we have the H5 files, we have the Python script ready to be deployed, blah blah blah. We need to test there prior to that. So with validation data set and with testing data set. But you also need to test another time. So when you're ready to deploy in real, in the real world, you need to test using the right architectures, the right data, the production data, because sometimes you will see gaps. You will deploy in a different way your model, so inference script. So what's an inference script? It's basically the way you are able to predict new data. So you need to build a new script. You can do errors in this new script, and the data had a problem in a fintech company. We're looking at transaction data on bank accounts. I was using data about expense and income, and the income, we add two columns, one for every incomes and one for every expense. It's easy. If it's in one, then it's an income, and if it's in the other, it's an expense. But the real data, what happened is it was only in one column. It was in the two column, but one was a negative number. I didn't know that. I was younger, didn't test it, and it was just crap. We deployed in the real world a crappy product because we didn't test the tiny last step that we should have done. Oh, okay. So, okay. So some questions that we can ask. This is just an example. So how was the data collected? On Kaggle, and this is really basics, just to give an idea. But like Kaggle, you get data sets. Sometimes you get data set and you don't have a lot of context around the data that you have. It's important to understand it, and also it's important to understand if you can even have the same data in production. Sometimes we think about we do a POC. So let's do the proof of concept. You do it, and then you realize that you cannot deploy it because the data doesn't exist. Another one is about some common scenarios happening after prediction. So, and here I want to connect with the third one. How are false positive and false negative biases represented? It's a little bit more technical, but I'll give you an example. I'm working with a telecom company, so we're doing churn prediction to avoid quitting and going to the competitor. The thing is, everyone who want to quit, they have two choices. They quit or they complain about them quitting, they get a discount, and then they're staying. So if you just want to do the project the dumb way, you don't ask those type of questions. You say, oh, I'll have a database for a given month. I have 90% of people who stayed with the company, so they are not churning this month. And maybe not 10% because they won't stay in business for a long time. But let's say they have 2%. Those are the the churners that you want to prevent. But you're lacking the layer of people who wanted to churn but didn't churn. So this is what helps you passing from a good product to a great product. And another question that you want to do is also what insight to provide to the end users. So often the end users will brainstorm about the ideas of what AI can bring to us. But in real life, how do they need the information to use it? This is often they will underestimate the number of insights that they require, and they will come at the last minute. You know what? I can't deal with this. Like this is a percentage. I can't use this to change my day-to-day work. Okay, so this don't want to spend time. I just want to spend time reminding people that if you really want to do a good job, you need to have this test data set. Or, you know, you can call it a validation data set, a test data set. But you need, so when you have a data set, you need to split it in three. One for training, the other one for validation. That's a classic. We know it. You read anything about data science, they will say this. But what we have the tendency to do is to try so many models, and then you grid search and you just make the machine work for like days until the best result happen. But you spend you tested so many different variations that you get a risk that you overfit on the training and on the testing data set. So this is why you need to have the last data set to confirm that it works well. And here we're not talking about like another 20%. So it's not like 20% of your data goes there, another 20%, and you only have 60% to test it, to train on it. You can keep a very minimal proportion, but you need to have it so it's a final validation. But I'll talk about the different dimensions that you need to test when you have your model. First, you need to test the bias and variance. I'm going to test it. I'm not going to explain how to test it because often we'll talk about overfitting instead. But there are ways to test that. If you want, you can talk to me after the talk. I can explain you how to estimate the percentage of bias and the percentage of variance in your model, so it helps to understand. But I'll explain what bias and variance is right after this slide. So what you want to test is the fit. This one, well, it's pretty classic. Are you overfitting, underfitting? But there are different ways. There are different ways to validate that. So we'll cover some some that are good to know, or just a refresher for some people. I'm going to talk about model comparison. I know it's not new, but I'm in the type of people who I skipped quickly into deep learning. So I learned all the other technique, but I said, it's so cool what you can do with deep learning, and you get those awesome results. But I started this year to go back into other models. And you do the comparison between older proven models, like logistical regressions, some sampler model. You get awesome benefit, and it's worth it to compare the two different approach or multiple different approach. Also, I'll talk about some discrimination bias. I'll explain a little bit. I won't go in depth. So if you have question, you can ask me the question after. But I'll cover some techniques on how to do that. This is useful to understand if you're racist or not. Not you, your algorithms, I mean. And finally, I'll talk about adversarial sensitivity. I want to finish with like a cool technology to test something super useful. So first of all, what's the difference between bias and variance? I know this is really basic, but it's useful to come back to it. So the bias is often associated to the quality of your input data, the features. It's not necessarily that your features are wrong. It's maybe that you don't have the right observations. Like the example I gave for, so if I remove those people, the people who ask for a discount, but they are not churning, you're polluting your data set. So you're making your algorithms tougher to converge, hence you're reducing the performance of your model, because they will they will have the exact same behaviors that a person who would churn would have. So what's happening when you have a high bias? We see it there. So your algorithm won't be able to perform well. So it will underfit. Variance is about the model capacity to, let's say, okay. The higher the variance, the more prone your model is to overfit, to learn the model by heart. This is bad because when it learns by heart, it means that any new information is going to return, it's probably going to return bad results. It's not able to generalize well the data. And the goal here is to be able to find the right balance. You never can have no bias and no variance. It's impossible. So this is why we like machine learning. It's because it's uncertain. It's probabilities. It's fun to work with uncertain uncertainties. So it comes back to it comes back at the end of the day about being able to measure the overfitting, underfitting, so the level of fit your model is. So if we're looking at deep learning, so there's something that we call epoch. The epoch is essentially the learning curve, learning rate. And what we want to see here is so the first graph is a distribution is a model which is underfitting. So it's not that bad when it underfits because at least you know what you're going to get. So the axis, so this is the error. So the lower the error, the better your model. So here, why I'm saying that it underfits, it's because typically the optimal time for stopping a model, stopping the algorithm from learning, is when it starts to flatten. When it reaches a plateau, usually it's when you should stop it. It's because it reaches the optimal spot, number of epochs. The thing though that you want to validate is not just the way the curve is the shape of the curve, but also you want to look at the gap between, so the ratio between validation and the training data, the training curves. Sorry about that. So the bigger the curve, the less. So usually when you have a big difference between training and testing, it's rarely good news. You really want to make sure that the ratio is acceptable. Maybe it's a problem with the type of sample that you have. So maybe it's the right sample, or maybe it has not learned the right way. So you want to validate that. You want to make sure that your curves are closer together. Okay, and here something particular. My validation, and those are real examples from consulting companies, from our customers. But the validation curve is better than the training. This is super weird, and it's quite important. And so this is also a bad sign. It as pronounced as that. It means that usually you don't learn the right way, and the problem was the algorithm, not with the algorithm, but the methodology. So the way we were creating the data set, there was something wrong in this, so that's why we had this problem. Okay, so it's not necessarily the way we had this problem, but it's good to do these type of things, these type of tests, because it enabled us to find out. Because otherwise it seems better. It's like, oh, validation is better. That's cool. No, it's not really cool. You should expect it to be the exact same performance. that better? So if we're looking at the second chart, this is a classic overfit. You see around the like 80 epoch, you see the two data sets, they're very close. That's a good sign. And around the 80th epoch, then it reached the maximum, the optimal learning it should do. Then every other epoch is just garbage. You see here, because the validation data set stopped learning while the training continued to try to learn. So this is classic overfitting. So when you test that in real life or with other type of data, you should not expect to have better results. You should expect to, in fact, have worse results. Okay, so that's it for model fit. So if we're talking about model comparison, so here, this is a type of exercise that we do. We create a big model. Oh, what's happened? Okay, I'll go there. I don't. Oh, okay, came back. Good. But no, now it's this time. Okay. So here, so what we decided to do is to create just a big loop. So we're doing a big random search with random configurations, and we're testing different algorithms. So we did one exercise for time series regression, for classification. You know, you can find some techniques that are better, that are a little bit more robust. And this is what we did. So we created, so the current model is often deep learning, just because nowadays the technologies are so good that it's really worth it to start using deep learning a lot, but you need to monitor it. So this is why we started to do that. And then we have simpler models, and we have the performance. So here we see that the current model, the deep learning model, was performing more. So it's great, but is it? Oh, okay. It's like it's a mystery. It's slightly better, but then when you start to look at the standard deviation, so when you do multiple tests, you can see the results, and then when the results vary a lot, it means that it's a little bit less robust. It's prone to vary in time. The training time, we know that when you have a very deep learning model, usually it requires more resource, GPUs, a lot of CPUs if you decide to use CPUs, but it's not super efficient to get good results. Not as like regressions, classical regressions, or other techniques that are a little bit more simplistic. Prediction time, this is a big difference. So here, for instance, when I tested this model, it was like a very complex model. Every prediction was taking 0.2 seconds. Sometimes we don't care. We do a batch like every night. We just do prediction for every customers. But in my particular case, so it was in programmatic marketing. So we had 60 milliseconds to do a prediction. That doesn't work. So this is why we tested something else, and then we were able to have something way better for our own purpose, prediction time. And also storage needed. So you need to think about it when you do something in production, because you need to call the model over and over. And when it's big, so it creates some transactions, so input, output, to be able to access it for prediction. Okay, so now I'm going to talk about discrimination in terms of features. So what I'm doing for discrimination, And I'm sorry, by the way, I'm bringing you like left and right, talking about so many different subjects. But this one is one of my favorite. At the end of the day, it's about being able to understand what's happening when you predict something. And I know that we're not at a stage yet where we can understand the reasons why a prediction has been made. But at least nowadays, we're able to understand the impact of every features on the prediction. So a technique that I'm suggesting you to use is a library called SHAP, S-H-A-P. What it does, it's very simple to explain. Even I might be able to explain it well in English, and this is not my first language. It's basically trying to rebuild a prediction with every features. Okay, so you're looking at the impact of every features to try to rebuild the prediction. So if someone has 92% chance of churning, and you have 600 features, so here 600 features, you are able to measure the marginal impact of every feature for one prediction. And then you can do it for every predictions in your testing environment, testing data set. And this way, you are able to understand the impact of the variable, so the importance of the variable. There are also other techniques, but SHAP is great because it's polyvalent. So you can use it for every type of models. So here, what I want to show you is the contribution of every variable. And the first one, you see here, it contributes to about 70% of every predictions on average. So what it means there is you have, so it's not really robust what you have. So it means that your feature one is changing slightly, the impact will be huge on the prediction. If you have a null, if something happened to that variable, and in fact, what's happening is 70% of the prediction is based on one variable. So first, there's something wrong for sure, because you wanted to have 600 variable, but most of the predicting power is in one. So this is problematic. And often, what we started to realize, we didn't write. So I started to write a paper on that, but it's just not there yet. So what we realize is often those discrimination case will be shown in those areas. So when there's discrimination, so like gender discrimination or ethnicity, racism, often you will see it because so every time it happens, you see predicting power is so high. So that when you start to monitor it, you start realizing that maybe there's something wrong the way you're capturing your prediction. And this is something that you need to monitor. If I come back to a real story, when I was doing the transaction for the fintech company, I was categorizing the different type of transactions of a person. And then I was looking at the propensity for the person to borrow money. Okay, so a credit scoring, basically. And what I realized is by doing these techniques, when there was one type of income, it was always refused. And when I started to dig around, I understood that this was a type of revenue provided by the government for Native Americans. So basically, it was racism that was hidden because it came from people in the financial institution. And it just, it's just a classic example, but there are so many examples of that happening. And if we're not monitoring it, we're just building racism within the algorithms and within the models. So yeah, I was really passionate, and this is why I put this slide. But now I'll skip to something else, something pretty cool as well. Not that discrimination is cool, but the fact that we're now able to, I need to be careful. The fact that we're able to get it now and to understand it, it's cool. I'm going to talk about how to be able to understand sensitivity within your model. So in the financial world, if you're doing a bet investing money, let's say, usually people will tell you, oh, you know what? To test the worst case scenarios, use 2008 financial crisis. This is a pretty good example, but it's just one scenario. So you're going to tell, you know what? My algorithm is so robust because at one point in time, it acted right. So no, you need to test a lot of different scenarios. And sometimes it's hard to find those. So instead, you can use something we call adversarial examples. So here, it's the example of adversarial examples. I'm sure you heard of it lately. So let's say you have a image recognition algorithm. You're able to predict a panda right there. But then you add a layer. So you add something we call noise layer into the same image. So here you still see a panda, but you've been able to fool your model, and now it thinks it's a gibbon. Personally, I don't know what's a gibbon, but what I know is that it's not the correct answer. And sorry, it's a kind of monkey. So it's not that bad. Sometimes it could have been like what's great with this. It could have been a car or anything. Because when you use deep learning, often we call decision boundaries, they're not linear. And sometimes you have weak spots. And you just change a little bit your data set with a little bit of noise, and then you're able to break your algorithm, your model. So here, it's not just the fact that it missed the prediction, but with a very high confidence. So you're able to break your algorithm pretty quickly with adversarial examples. So what I'm using two different methods to test the sensitivity. So first, I'm using random noise. So let's say I'm taking my data set, forget the image, okay? It's like an Excel spreadsheet. And then I just change the noise. I just change the data by adjusting a little bit the values up and down, and then I'm trying to different level, okay, to see what's going to happen if I'm getting bad data quality. But I'm also doing the exercise of testing the same amount of noise, but when it's pinpoint by using adversarial techniques. And so what I'm able to see, sorry, 2 minutes. Okay, I'm going to be able to do it. Good. So here, this is the example. So when I'm testing the two methods on my model, so the first one, the orange line, you see that, so my model is good with, it's pretty good. So if when I'm deploying my model, the values are a little bit inexact, or it's robust to bad data quality. But then you see my errors is going through the roof super quickly. Adversarial examples. So what it tells me is that my model is not good at all when it comes to worst case scenarios. So now that I know that, maybe I will decide not to change my model, but I need to monitor it. I need to make sure those scenarios are covered by my model. Maybe I even create a rule. When this happens, or when it seems to be a bad scenario happening, then I don't predict it because I will get it wrong. So this is it. If you have any question, feel free to come and see me. You can talk to me. You can also connect with me on LinkedIn, and we can have discussions. I'm passionate about this. But you know, at the end of the day, when people will stop just using accuracy for, you know, an indication of performance, I think we'll be better off. And it's not super complex. We just need to think, and we just need to understand that a good quality, like a good validation on the test set, it's not enough. We need to think: are we doing the right thing? Are we deploying the right stuff for the end users? And are we making sure that when it's going to be deployed, it's going to be deployed the right way to see the same result we've seen in the proof of concept on real cases and affecting real people. So thank you very much.